There we go. All right, so this is going to be the quick version of the immune system since we did most of it yesterday. As soon as the screen comes back up. All right, there we go. So we talked yesterday about there being two main parts of your immune system, the non-specific or innate. That's the part that's built in, you're born with it, you don't have to do anything to get it. And then the specific, or sometimes it's called the acquired immune system. So just with the non-specific, things like skin, inflammation, your stomach acid, the normal flora, which are your natural what? Bacteria. You've got chemicals like lysozyme in your saliva and your tears. You've got your mucous membranes. And you've also got these proteins that cause you to get a fever when you get sick. All those things are non-specific. They just protect you against germs in general. But what we want to focus on here quickly is the specific or the acquired part. And I want to use this diagram, and this will run us through most of it. There's two parts of the specific immune response. There's the humoral, sometimes called antibody-mediated immune response, and there's the cell-mediated immune response. Why is the humoral called humoral? Yeah, it can only work against germs that are in the fluids, in the blood, in the lymph, in the fluids between the cells, because what are antibodies? They're big old bulky proteins and they can't get into cells very easily. So with the antibody-mediated response, just a quick summary, an antigen gets into you. What's an antigen? Foreign protein. Could be on a bacteria, virus, fungus, worm, whatever. That antigen gets engulfed by some kind of phagocytic cell, usually a macrophage. It phagocytizes it, uses the lysosomes to intracellularly digest it, and then it displays the antigen, some of those pieces of that germ, on what structure? What do macrophages display antigens on? MHC2. And they display those antigens mostly to helper T cells. But only helper T cells capable of doing what? Yeah, docking with that antigen. They have to fit. They have little receptors and they have to fit. When they fit to this macrophage, they're communicating, and it's essentially saying, hey, this thing was in me, I killed this one, but here's a piece of it. You need to send out the message to other parts of our immune system to kill some more of them. And we keep comparing the helper T cell to Paul Revere, because that's sort of the helper T cell's job, to send out the message. It sends out these chemicals called interleukins. Eventually it'll catch up with me. Interleukins, or sometimes they're called cytokines. And those cytokines, or interleukins, are messages to B cells in this case. And they stimulate them. But they only stimulate ones specific to what? That particular antigen. Ones that are capable of making antibodies that will kill that thing. And the first message to these B cells is to do what? What do those B cells have to do first? Copy themselves, clone, make a bunch of copies of yourself. That's number one. And then most of those B cells turn into what are called plasma cells. And they're called plasma cells because they have a whole lot of what organelle? Rough ER. And things with a lot of rough ER are mostly doing what? Making proteins, and then doing what with the proteins they're making? Shipping them out. And the proteins they're making in this case are antibodies. Antibodies specific to that particular antigen up there at the beginning. Also remember though that some of those cells never turn into plasma cells, they just hang around as memory cells. We'll come back to those in a minute. Remember that the antibodies work by essentially binding to the antigen, and they can either like mark it for death, causing other cells to kill it. They can be like a handle, which can be used to help to escort the germ out of the body through what system? The urinary. They can cause the germs sometimes to clump up, so they're easier to get rid of. Antibodies don't usually kill a germ by themselves. You might think of them as like marks for death. All right, that's your antibody-mediated system. Remember, though, that can only help if the germ is between cells in the fluids. The other part of the system is the cell-mediated. And this is when your immune system kills what? Your own cells that have an internal infection, an intracellular infection. And the way that works, how does your immune system know that that cell is sick? Yeah, it displays proteins from inside itself on an MHC1. And if it has a virus or if it's cancerous, some of those proteins that it's displaying are probably kind of weird. And that's going to stimulate helper T cells and cytotoxic T cells. And I compared those cytotoxic T cells to what comic book character? Wolverine. They'll find cells displaying those bad antigens, and they'll essentially poke holes in their cell membranes and kill them. Once this is over, again, there's memory T cells, there's memory helper T cells, there's memory B cells. And those will help with what response later if this comes around again. What do we call it the next time? Secondary response, which is much what? Quicker and bigger. There's a bigger response. It's a bigger, faster response. These two systems together, though, make up your specific or acquired immune system. Let's see, something else I wanted to point out to you. Remember that antibodies are proteins. Remember they work a lot like enzymes, and that there's a little site, almost like an active site, and that antigen has to fit in there. And if it doesn't fit, that antibody doesn't work. That's why they're very specific. And that's kind of showing you the same thing. Just looking for one more diagram here. So, important diagram. The first time you get sick, the levels of antibodies in your blood, in your plasma, take a long time to go up, and they don't ever really go that high. But by the time the antibodies levels get to maybe right in there, you're probably okay. So the levels start to drop, because what happens to those plasma cells after you start getting well? Yeah, they do apoptosis, they self-destruct, they die. So your antibody levels drop, and they drop down to almost zero. But what's still in your blood? Memory cells. And how long do they stay there? For the rest of your life, probably, in most cases. So let's say here you get exposed to the germ again, right in this point. Your immune response is so fast and so big the second time around that you probably don't even have symptoms. That's your antibody response. It's also your cell-mediated response. So together they're working really fast because now they know what the germ looks like, they know how to kill it, and they kill it fast, so big, so fast, you probably don't get symptoms. So secondary immune response versus primary immune response. Questions? All right, main thing I want to look at today then to get us a little ahead of schedule is the urinary stuff. Give me a minute to switch over to that. All right, there we go. So with the urinary system, one of the big things about the urinary system, one of its main jobs is osmoregulation, which is regulating what? Your water and solute balance in your blood, osmoregulation. So we talked about that already. Its job is to keep a balance between salts and water. Another job is to remove waste. In particular, what kind of wastes? Nitrogenous, which you generate when you eat what? Proteins. So remember the whole protein deal. Here's an amino acid. When you eat a protein, you first break it down into amino acids. Then what do you do to it next? You break that off. That's called the amino group. And it really quickly attaches up with the hydrogen that's just floating around a proton, and it becomes this. That's what chemical? It's ammonia. This then, though, runs through what system? This part. You go through the Krebs cycle, it can be used to make ATP and stuff. But this is a problem because it's really, really, really wet. Toxic, and it's also what kind of chemical? It's a base. So it's toxic and it can change your pH. So you got to have a way to deal with it. If you're a fish, how do you deal with it? Yeah, your kidneys filter it out and you're just urinating all the time. So every time you make it, you urinate it out. That works for fish because water's not a problem for them. But for a land-based animal, if you're urinating all the time, you're going to dehydrate. So that won't work. So for mammals and amphibians, the way we deal with it is our liver, first of all, will take this ammonia and do a little fancy chemistry on it. Let me go to another slide here. So here's ammonia in us, in mammals and amphibians. Our livers convert it to that, urea, which is a little less what? A little less toxic. Still toxic, but not as toxic, which means we can hold on to it for a while. Eventually, our kidneys will filter it out and we'll have to urinate it out. It's still very soluble in water, so when you urinate it out, you lose some body water. On the other hand, animals that develop in a hard-shelled egg, like reptiles and birds, would that work for them, the urea solution? No, because when you're in an egg, you're still breaking down proteins, right? Which means you're still generating ammonia. And if you turn it into this is water soluble, what's going to happen to you if you're in an egg? You're going to poison yourself because that's still poisonous. And it can't get out of the egg. So instead of doing urea, their liver converts it to a different thing, uric acid. And the solution about this is this is just not very wet. Yeah, it's pretty much insoluble in water. Which means when it's made, it does what? It precipitates out, and it's not going to hurt the developing baby because it's not in the liquids. It precipitates out. So again, this is the solution for fish. Just urinate out ammonia. This is the solution for amphibians and mammals. Why does this work for amphibians? Yeah, their egg is just this jelly-like thing, right? And that stuff can go straight out of it. It's not a problem. But birds and reptiles have the hard-shelled egg that can't get out. So they can create this instead, and it'll build up and just sort of precipitate off to the side. Yeah. I would assume monotremes do uric acid. Don't quote me on that, but that would be my assumption, because that wouldn't work in monotremes either. It's a good question. I assume that's the case. And this is just showing you fish just urinate out ammonia. Mammals, amphibians, some bony fish, not many, make urea. Birds, most reptiles, some insects make uric acid. So let's talk about how urine is made here. This is the nephron. There are thousands of these in every kidney. And they're essentially what? Filters. Sometimes they're called the functional units of your kidney. And the way it works is you've got a blood vessel, a little arteriole, coming into the nephron. The nephron's this yellow part. And it branches into a bed of capillaries inside this big funnel-shaped thing. That bed of capillaries is called the glomerulus. What do we know about capillaries? They're usually what? Leaky. And these are really leaky. So when the blood goes into this bed of capillaries, most everything leaks out except the cells themselves and some water and stuff. That's step one of making urine. And it's called what? Filtration. It happens there at the glomerulus. And good stuff and bad stuff get filtered out. The urea comes out, but some water comes out. Nutrients come out, amino acids come out, sugars come out. All kinds of stuff comes out of your blood vessels into what's called the renal tubule, or the nephron, this yellow stuff. From the Bowman's capsule, which is the big funnel-shaped head, the liquid starts to move through the tube. What's the name of the liquid that came out of the blood? What's it called? All the stuff that came out of the blood is called what? It's called filtrate. Same word you might use for the stuff you run through a filter in chemistry. Filtrate. And remember that most of that filtrate, what do we want to do with most of it? We want to put it back in the blood. And that's where step 2 comes in. What's step 2? What's step 2 of making urine? It's called tubular reabsorption. And reabsorption happens mostly in the first part of this tube, which is called the proximal tubule. And we've been calling it proximal what? Convoluted tube, because it's all curvy. It also continues to happen in this U-shaped part here, which is called the loop of Henle. The water, most of it goes from the tube back into the blood simply by what process? Yeah, osmosis. That's passive. But a lot of the nutrients, things like vitamins, sugars, how do those have to be put back into the blood? Active transport. They're pumped. So there's all kinds of little carrier proteins in the loop of Henle and in the proximal tubule, whose job it is to grab things that you need to keep and pump them from the tube and back into these blood vessels. It's called tubular reabsorption. And then the final step is called tubular secretion. And most of the secretion happens in the last part of that renal tubule called the distal tubule, the distal convoluted tubule. And here, let's say that you're having pH problems. Maybe your pH is too acidic in your blood. What could you do to raise the pH back up? Here. What happens here that might help your pH? What happens in tubular secretion? Stuff that's in the blood that you need to get rid of can be pumped, actively pumped from the blood vessels into this renal tubule. And one of the main things that gets secreted that way is H+. If you got too much H+, your body will move it from the blood vessels into the tube, which means you're going to urinate out the H+. And if you lose H+, what happens to pH? It goes up. So those are the 3 steps of making urine. Eventually, the urine will leave the renal tubule and it'll go into what's called a collecting duct, which eventually all the nephrons will dump into these ducts, and they'll lead to the last part of your kidney, which is called the renal what? The renal pelvis. It looks like a big funnel, and it will dump into what tube that leaves the kidney? What's the tube that leaves the kidney called? The ureter, and that'll take the urine to the bladder, and then what tube takes it out of the bladder and eventually out of the body? The urethra. Couple of things to think about here. There's some desert animals, like there's this little rat called the kangaroo rat. A lot of the desert animals, first of all, how do they mostly secrete their nitrogenous waste? What chemical would most desert animals secrete nitrogenous waste as? Ammonia, urea, uric acid. Uric acid, because that means their urine comes out kind of pasty, right? They don't lose much water. But another thing that's kind of neat about some of those desert animals is that for their body size, this part of their nephrine is way longer or way shorter than a normal animal. Way longer. And that's important because what happens in Lupa-Henle? Reabsorption. So they take more and more water out of the urine so they don't urinate much water out. It's a way to conserve water. A lot of desert animals have this really enlarged, long Lupa-Henle. There's one more slide I wanted us to look at here. Actually, two more. ADH. What's ADH stand for? Anti-diuretic hormone. Where's it made? The pituitary. And when does your pituitary release a lot of it? Yeah, when you're starting to dehydrate. Maybe you're exercising, you've been sweating a lot. Maybe you just haven't drank much water. Maybe it's just really hot. For some reason, you're dehydrating. So the pituitary releases ADH, and it goes out and affects what? What part of the nephrine does it affect? Yeah, it affects mostly the distal tubule here and the collecting ducts. And it makes them more, Matthew, let still in, please. More or less permeable to water. More permeable to water, which means the water that's in these tubes can now come out of these tubes and go back to where? The blood. So it helps to conserve water. Remember, a diuretic is something that makes you what? A diuretic makes you urinate. So anti-diuretic hormone slows down urination, which you're wanting to do if you're dehydrating, right? Because you want to keep water in. All right, one more slide here on this, essentially. All right, this slide I'm not sure that we've seen before. Some adaptations that different animals have for conserving water, different organisms have for conserving water. Keratinized skin, for example. What's keratin? It's protein. It makes your skin waterproof, essentially. Reptiles have it. It's the main part of what part of a reptile? It's what their scales are made out of. Birds have it. Mammals have it. Really important for making you waterproof, keeping water in your body. Insects don't necessarily have keratin, but they have an exoskeleton, which really serves the same function, right? It's like an external layer to keep water in them. A lot of animals are nocturnal, only come out at night. That's important. Sort of like what plants? Cam plants, right? Because other plants, what do they do at night? They close their stomach. The cam, they close them in the day, fixed carbon at night. They're sort of like nocturnal animals. A lot of organisms have storage cells or vacuoles to hold water. What's the most famous example of that? Something that has vacuoles. Well, camels, that's not really a vacuole, but what's the big vacuole we talked about over and over again in this class? What cells have the big old vacuole in the middle? Plants, right? Plants have a big central vacuole to store water. But there are some desert animals, like camels, that have places to store water. That's true. The waxy cuticle, which we know is on plants, acts like a coat of skin, essentially. And there are some marine animals that have these things called salt glands. And the salt glands pump salt out of their body. Why would you want to pump salt out? They live in a really salty environment, and if they have too much salt, what else are they going to get too much of? Too much water, because water moves to where there's more solids, right? Toward solids. So those are just a few adaptations that help things to retain water. There are also different animals that are called either osmoconformers or osmoregulators. Which one do you think you are? You're an osmoregulator. That means you are actively doing what? You're actively maintaining a certain balance between what? Solids and water. There are some animals that if you put them in salty water, what happens? Well, yeah. That really wouldn't count here, though. Some of them, they just become salty, and they're okay with that. And it works. That's an osmoconformer, that their body's salt concentration and water concentration changes with the environment. And there's a few of those. But most animals are osmoregulators. We have to maintain a certain concentration of water and salt. If we don't, we're in trouble. Does that make sense? All right. Stop that. Yesterday we did a little bit of statistics in here. We're going to do a little bit more here before we go.